calculations presented appear generally correct. Here is a review of the calculations and some additional considerations. Firstly, lighting and outlets are calculated at 45,000 volt amps, which is determined by 1400 square feet times 3 volt amps per square foot times 6 units. Secondly, appliances, specifically two-wire circuits, are calculated at 54,000 volt amps, derived from 6 units times 1500 volt amps times 6 units. Thirdly, air conditioning units contribute 21,600 volt amps, based on 30 amps times 208 volts times 6 units. Finally, electric stoves account for 62,000 volt amps, calculated as 50 amps times 208 volts times 6 units. The total load is therefore 382,600 volt amps. As per National Electrical Code Table 220.84, the demand factor for 6 to 7 dwelling units is 44%. Applying this demand factor, the demand load becomes 382,600 volt amps times 0.44, equaling 168,944 volt amps. Converting this to amps, it's 168,944 volt amps divided by 208 volts, which equals 812 amps. The calculation suggests a 400 amp service, which is generally sufficient for a 6-unit apartment building. However, it's important to consider several factors. Firstly, voltage drop must be considered. Ensure that the voltage drop from the service to the furthest load does not exceed 5%. Secondly, future expansion needs to be considered. Account for potential future loads, such as electric vehicle charging or additional appliances. Thirdly, National Electrical Code requirements need to be met. Verify that calculations comply with all applicable National Electrical Code requirements, including Article 220. Feeder sizing should be based on the ampacity of the conductors and the length of the feeders. Calculate the load on each feeder and select conductors that can handle the current without exceeding their temperature rating. There are also additional considerations. Ensure that the service and feeders are properly grounded in accordance with National Electrical Code requirements. Install appropriate circuit breakers or fuses to protect the conductors and equipment from overcurrent. Create panel schedules to indicate the devices and loads connected to each panel. Overall, the calculations appear to be reasonable for a 6-unit apartment building. However, it is recommended to consult with a licensed electrician to verify calculations and design, especially if there is a lack of experience in electrical design. A more detailed breakdown of the load calculations and the code references might be helpful. Firstly, consider the general lighting and receptacle load. As calculated, this is 1400 square feet times 3 volt amps per square foot times 6 units, equaling 25,200 volt amps. This covers the basic electrical needs of each apartment. Secondly, small appliance circuits should be considered. The National Electrical Code requires at least 2 20-amp small appliance branch circuits for the kitchen and 1 20-amp laundry circuit. Each 20-amp circuit is calculated at 1500 volt amps. So for each apartment, that's 3 circuits times 1500 volt amps, equaling 4500 volt amps. Multiply this by 6 apartments to get 27,000 volt amps. Thirdly, individual appliances need consideration. In this case, there are electric ranges and air conditioning units. Electric ranges are typically calculated at a demand factor, according to National Electrical Code Table 220.55. However, since the provided calculation uses the nameplate rating, we'll stick with that for consistency. Air conditioning units are calculated based on their nameplate ratings which were given. Fourthly, space heating, if applicable, should be considered. If the units have electric space heating, that load needs to be included. This can be significant, especially in colder climates. Fifthly, water heating also needs to be considered. If the units have electric water heaters, those loads should be included. Sixthly, other fixed appliances need to be considered. This could include things like dishwashers, garbage disposals, or other permanently connected appliances. Each of these should be added to the load calculation at the nameplate rating. The National Electrical Code provides methods for calculating the service demand load for dwelling units, including options in Article 220 Part 3. The standard method is outlined in 220.82, and the optional method for multifamily dwellings is in 220.84, which was used. The optional method allows for a demand factor to be applied to the total connected load, recognizing that not all loads will be on simultaneously. Remember that local amendments could change the requirements. The calculated load of 812 amps might seem high, but it's important to remember that this is a calculated demand load, not the actual load that will be drawn continuously. The 400 amp service may be adequate, but it's crucial to verify all the assumptions and calculations. Also consider that the 208 volt is likely a 208/120 volt three-phase service. The calculations treat the entire load as if it was single-phase 208 volt, which simplifies the math but might not be entirely accurate. It would be more precise to calculate the load on each phase, taking into account the phase voltages and the distribution of loads. To perform a more accurate calculation, consider the following steps. Firstly, determine the actual voltage configuration. Is it 208/120 volt three-phase or some other configuration? This affects how the loads are balanced and calculated. Secondly, allocate loads to phases. Distribute the 208 volt loads, such as ranges and air conditioning units, as evenly as possible across the three phases. The 120 volt loads are automatically balanced to some extent. Thirdly, calculate the load on each phase separately. For each phase, add up the volt amps from lighting, receptacles, small appliance circuits, and any other loads connected to that phase. Fourthly, apply demand factors as appropriate. Use National Electrical Code tables to apply demand factors to different types of loads, such as ranges and air conditioning units. Fifthly, calculate the total demand load for each phase. This is the sum of the loads on each phase after applying demand factors. Sixthly, determine the service size. The service size must be large enough to handle the largest phase load, plus any neutral load. Also, consider future expansion. If there's any possibility of adding more loads in the future, it's wise to upsize the service accordingly. Electric vehicle charging is becoming increasingly common, and it can add a significant load to the electrical system. Remember that the National Electrical Code is a minimum standard. It's always a good idea to exceed the minimum requirements to provide a margin of safety and allow for future growth. Also consider the quality of the power supply. If the building is located in an area with unreliable power, it might be wise to install a backup generator or other power conditioning equipment. Finally, document all calculations and assumptions. This will make it easier to verify the design and make changes in the future. When calculating the service and feeder size for a multi-unit dwelling, there are a few more crucial aspects to consider. Firstly, diversity is key. Not all units will be using their maximum power at the same time. National Electrical Code Table 220.84 allows for a demand factor to account for this diversity, especially for multi-family dwellings. Make sure to apply the correct demand factor based on the number of units. Secondly, load balancing across phases is important. In a three-phase system, unbalanced loads can lead to voltage imbalances and increase neutral current. Strive to distribute the loads evenly across the three phases to minimize these issues. When calculating the neutral load, remember that not all loads contribute to the neutral current. For example, 240 volt appliances connected line to line don't have a neutral connection. The neutral load is primarily due to 120 volt loads connected line to neutral. Also, harmonic currents generated by electronic devices can increase the neutral current, so consider this if many units have computers, televisions, and other electronic equipment. Thirdly, voltage drop calculations are essential. Excessive voltage drop can cause lights to dim, motors to run poorly, and electronic equipment to malfunction. Calculate the voltage drop from the service entrance to the farthest unit under peak load conditions. If the voltage drop exceeds 3% for feeders or 5% total, you'll need to increase the conductor size. Fourthly, conductor ampacity and overcurrent protection need to be properly considered. The conductors must be sized to carry the calculated load current continuously without exceeding their temperature rating. Overcurrent protection devices, such as circuit breakers or fuses, must be sized to protect the conductors from overload. Make sure the overcurrent protection device rating doesn't exceed the conductor ampacity. Fifthly, grounding and bonding need to be considered. Proper grounding and bonding are essential for safety. The grounding system provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. Sixthly, coordination of overcurrent protection devices is important. If there are multiple overcurrent protection devices in series, they should be coordinated so that the device closest to the fault trips first, minimizing the extent of the outage. Selective coordination can be achieved by using fuses with different time current characteristics or by using circuit breakers with adjustable trip settings. Also consider accessibility and working space. The National Electrical Code requires adequate working space around electrical equipment for safety and maintenance. Make sure there's enough room to access the equipment for inspection, testing, and repairs. Also consider future expandability. It's often wise to provide extra capacity in the service and feeders to accommodate future load growth. This can save you money and hassle in the long run. Finally, documentation is very important. Keep accurate records of all calculations, drawings, and specifications. This will be helpful for future maintenance, modifications, and troubleshooting. Remember that the National Electrical Code is updated every 3 years, so make sure you're using the latest edition. The National Electrical Code is not a design manual, it's a safety standard. It provides minimum requirements for electrical installations. A qualified electrical engineer or electrician should be involved in the design and installation of the electrical system to ensure that it meets all applicable codes and standards and is safe and reliable. To reiterate, a few other very important points should be emphasized. Firstly, demand factors for ranges should be considered carefully. National Electrical Code Table 220.55 provides demand factors for household ranges and ovens. These demand factors can significantly reduce the calculated load for the service and feeders. However, the notes to the table should be carefully considered, as they may limit the applicability of the demand factors in certain situations. Secondly, air conditioning and heating loads should be considered together. In many climates, both air conditioning and heating loads are present, but they don't operate simultaneously. The National Electrical Code allows the smaller of the two loads to be omitted from the service calculation. However, it's important to consider the climate and the operating characteristics of the equipment to determine which load is smaller. Thirdly, electric vehicle charging loads should be anticipated. As electric vehicles become more popular, the demand for electric vehicle charging stations will increase. If the apartment building has parking spaces, it's likely that residents will want to install electric vehicle chargers. Each charger can add a significant load to the electrical system, so it's important to anticipate these loads and provide adequate capacity in the service and feeders. Fourthly, emergency and standby power systems should be considered. If the apartment building has emergency or standby power systems, such as generators or battery backup systems, these systems must be properly sized and installed. The National Electrical Code provides requirements for emergency and standby power systems in Article 700 and Article 701. Fifthly, coordination with the utility company is very important. The utility company will typically have requirements for the service entrance equipment and the connection to the grid. It's important to coordinate with the utility company early in the design process to ensure that the electrical system meets their requirements. Sixthly, proper labeling and documentation is essential. All electrical equipment must be properly labeled to identify its function and voltage. The electrical system should be documented with accurate drawings and specifications. This will be helpful for future maintenance, modifications, and troubleshooting. Seventhly, ongoing maintenance and testing are essential. Electrical equipment should be inspected and tested regularly to ensure that it's operating properly and safely. This includes inspecting conductors for damage, testing overcurrent protection devices, and verifying the grounding system. Also, be aware of energy efficiency requirements. Many jurisdictions have energy efficiency requirements for new buildings. These requirements may affect the design of the electrical system, such as the selection of lighting fixtures and appliances. In summary, the service and feeder size calculation for a multi-unit dwelling is a complex process that requires careful consideration of many factors. It's important to consult with a qualified electrical engineer or electrician to ensure that the electrical system is safe, reliable, and meets all applicable codes and standards. This narration is for informational purposes only and should not be considered a substitute for professional advice.